Welcome to this talk. This work was done jointly by Jiaxin and myself, Magnus Ringerud. Our title is Signatures with Tight Multi-User Security from Search Assumptions. In this talk, I will talk about digital signatures, some of the motivation behind our project, a few technical details, and finally a conclusion to our work. A digital signature is a scheme that has three algorithms. A key generation algorithm, which takes a security parameter as input and outputs a public and a secret key. A signing algorithm, which takes a message, a secret key, and outputs a signature. Finally, a verification algorithm, which takes a message, a signature, and a public key as input, and it outputs whether the signature is a valid signature or not. When we argue security for schemes like this, we use security games. And for a single user signature scheme, this is the most used security game, and it is called the unforgeable against chosen message attack. And the challenger will generate a key pair. He will send his public key to an adversary. The adversary can then ask for signatures on any chosen message he desires, and the challenger will respond with a signature. Finally, the adversary will submit a forgery, and he will win if the message that he submits is different from all the messages he has sent previously, and the signature verifies. Now, this is in the single user setting. As I mentioned, this is often called the single user unforgeability against chosen message attack. And often we just call it unforgeable against chosen message attack, and we drop the SU prefix. Now, in the real world, there are many users, or there might be many users, so an adversary might be exposed to many public keys. And it could happen that he just wants to forge on any single one of them, not a specific one. And that brings us to the multi-user setting with the security notion multi-user unforgeability against chosen message attacks. And this is a security game. We highlight with red the differences. So notice now that there's many public keys, and whenever the adversary wants to get a signature, he also appends the index of the user that he wants the signature to be under. The challenger will then sign with the corresponding signing key and return the signature. And as before, after some time, the adversary has to submit a signature, which he now also submits under a specific user. And different from before is that if he has already received a signature on a specific message, he can still reuse the same message as long as the user is different in his final forgery. Now, when we argue security like this, we use a security proof to formally argue. And security proof is a reduction that relates the security of the scheme to the hardness of some mathematical problem. And we say a reduction is tight if it closely relates breaking the scheme to breaking the mathematical problem. And tight reductions enable us to choose security parameters at a concrete security level, which can mean smaller parameters and faster computations. So this has a practical implication as well as theoretical. An earlier work on secure or tightly secure signatures, and where we base our work on, is by Kills, Masny and Pan, and Kills, Loss and Pan. And the first one is they derived signatures from three-move identification protocols via the Fiat-Shamir transform. And there they were able to create tight reductions from multi to single user protocols. And I found an optimal but not tight reduction from single user to a computational problem. And now, if we assume a stronger decisional assumption, the reduction I found is tight. And so for the other work, I started at the 5-move identification protocols, And there they found type reductions from a single user to a computational problem, but no type reduction from multi to single user. So this is where this work starts. Other work in this area is the full domain hash with a tight proof, and this is only in the single user setting, all of this, and all of the above is also in the random oracle model. There has also been done work in the standard model, but those are all based on decisional assumptions. And currently there is no known tightly secure multi-user scheme based on a computational assumption. Now I've said a lot about decisional and computational, so I'll talk some more on that or explain it. So this is one of the most famous computational problems. It's the computational Diffie-Hellman problem, where a challenger chooses two numbers and he sends g to x and g to y for some generated g of a group, and the adversary then has to compute g to xy in order to win the game. Now compare this to the decisional variant, where an adversary instead has to distinguish whether this ZB that he has gotten is actually g to xy or just random. So notice that if he could solve the computational problem, he could just compute g to xy and check for himself. So the decisional problem is easier, or at least not harder, than breaking the computational one. And this is the case for all computational versus decisional assumptions that relates in this kind of way. And to be formal, a computational assumption is weaker and hence better than a decisional assumption. And for example, there exists a group where the computational Diffie-Hellman is equivalent to the discrete log problem, which is not equivalent to this decisional Diffie-Hellman. So there is a difference in difficulty. And until now, all known multi-user schemes had either a tight reduction to a decisional assumption or a non-tight reduction to a computational assumption. And so our contribution is then a multi-user signature scheme, or multi-user signature schemes with tight reductions to computational assumptions. And they are more efficient than Schnorr and ESA at the concrete level. So asymptotically, they're more or less the same, but at concrete level, ours are better. Our solution uses key prefixing on schemes from this KLP paper, the 5-move identification protocol. So, technical details or overview. This is the model we had earlier, which is the chosen message attack. We want to simplify this a bit in our explanation here. So we remove the signing part and we look at the key-only attack, where an adversary receives all the public keys and he then has to come up with a forgery. Now, this is an illustration of our reduction. The challenger plays a single-user game with the reduction, and the reduction plays a multi-user game with the adversary. So the challenger will generate his own key pair and he will send the public key to the reduction, who then uses the structure of the schemes to re-randomize this and obtain new public keys, which he will then forward to the adversary. Now, the adversary can now ask for random oracle queries, and the reduction can choose whether it wants to program or then change the contents of this or just forward it to the random oracle that is provided by the challenger. And after some point, the adversary has to provide a forgery, which the reduction then has to modify in some way. Look at the adversary sends a forgery and this I star, which is the user that it has forged on. The reduction now has to modify this so that the new forgery is valid under the original public key of the challenger. And so there's a problem here, and that the signature is of the form sigma equals RL age and S, where the discrete log of RL to the base age is equal to the discrete log of the public key to the base G, which is then the signing key. And age and S is a non-interactive zero-knowledge proof of this. It's not important to know what the non-interactive zero-knowledge proof is, but it's essential to know that it proves the above assertion, that these discrete logs are the same. So in the reduction, we want to map a multi-user forgery, which we denote with stars, to a single-user forgery, which we denote with tildes. And for a valid single-user forgery, we require that this age prime of whatever the adversary gave us his forgery has to be equal to age of whatever the reduction spits out. And since this RL is directly related to the secret key, these will change when we move from forging on one user to another. And hence, this equality will never happen, since these two things won't be equal. If that were to happen, we would have found a collision in the hash function if all we did was forwarding. So as you can see here, this is the illustration of you just forwarding x and age of x back and forth. Then you'll never be able to turn the adversary's forgery into one against the challenger. So what we did instead is that we programmed the input to this random oracle to make sure that for the forgery, the hash outputs are consistent. And to do this, we include the public key of the user which you send out the message under. And we also include some more information in the hash function age and age prime. This allows us, in a simple way, to control which messages we need to choose or need to change, and which that we can simply forward. The public key is there as a flag to show us now we need to change this. And if they simply ask for the hash of something random, we just forward it. And then to conclude, this all gives us tightly secure multi-user signature schemes. One of our schemes, the most efficient one, is essentially equal to a previous scheme, which I will not try to pronounce, but with an improved proof. Their proof is for the single-user scheme, while ours is in the multi-user. And our scheme is roughly twice as efficient as Schnorr at a concrete level. So from this table, you'll see this is an estimation for 128-bit security. And since Schnorr and DSA have non-tight proofs, they have to compensate for the number of estimated signatures. And to do this, they'll move to curves that are slower. Ours is tight and not dependent on the number of signatures, hence it doesn't need to compensate like this. And once the numbers get truly large, our scheme is faster. The bottom schemes are based on decisional assumptions, which is why the Katzwang is very fast, but then also has a stronger assumption. All the top ones are based on search assumptions or computational assumptions. For future work or open problems here would be to include corruptions where you have secret key leakage. And it would be interesting to try and remove the random oracle model, but still be able to keep a search assumption. That is it.